We have found a new particle never seen before in Mother Nature by slamming two beams of proton at trillions of electron volts. What if the world's most powerful machine just pushed reality past its breaking point? Right now, deep beneath the Swiss-French border, CERN's Large Hadron Collider is smashing particles at energies humanity has never achieved before. We're talking 13.6 trillion electron volts. That's enough power to recreate conditions from the first trillionth of a second after the Big Bang. And renowned physicist Michio Kaku says CERN's newest collision data may have shaken spacetime itself. Here's what's keeping scientists awake at night. In 2024 alone, CERN recorded over 10 million billion particle collisions. That's an unprecedented dataset. But buried in those numbers are anomalies, tiny deviations that don't match our theories. The strangest part? We already have data hints that something unusual might be happening. Stay with me here. This isn't about wild portals or science fiction movies. We're talking about real experiments, real anomalies, and real scientists asking if the fabric of reality is starting to show stress fractures. Just this year, CERN's CMS experiment ran the most sensitive test ever on Einstein's spacetime rules. They were looking for any crack in reality's foundation, any sign that our universe has a preferred direction, any hint that spacetime itself might be breakable. And what they found changed everything we thought we knew about the limits of physics. But before we dive into those results, you need to understand exactly what CERN is doing down there that has physicists both thrilled and terrified. Here's what most people don't realize about spacetime. We think of it as this smooth, invisible fabric stretching across the universe. Einstein showed us it bends around massive objects like planets and stars. But some physicists now believe spacetime isn't smooth at all. Picture the surface of a calm lake from far away. It looks perfectly flat. But zoom in close enough and you'll see ripples, waves, and tiny bubbles. That's exactly what leading quantum theorists think it might be like at the smallest scales. They call it quantum foam, a grainy, bubbly structure that only becomes visible when you probe it with incredible energy. And that's exactly what CERN is doing. Every collision in the Large Hadron Collider is like smashing two bullets together at nearly light speed. These aren't just particle crashes, they're stress tests on the fabric of reality itself. Think of it this way: if spacetime has a hidden texture, these collisions might be the first time in human history we're hitting it hard enough to feel the bumps. This isn't just theory anymore. CERN's data is showing us something strange. Remember 2015? Scientists detected what they called a diphoton excess, a tiny bump in their data at 750 billion electron volts. For months, physicists worldwide held their breath. Was this a new particle? A crack in our understanding? It disappeared with more data. False alarm. But here's what's terrifying and exciting. Run 3 data from 2023 and 2024 is revealing new tiny bumps, different energies, different patterns. Most scientists are calling it statistical noise. But some are asking a darker question. What if these aren't random fluctuations? What if they're early signatures of spacetime starting to show stress fractures under CERN's relentless pounding? The muon G2 experiment at Fermilab already showed us that particles don't behave exactly as our theories predict. There's something missing in our equations, something we haven't discovered yet. But there's another mystery, something happening right now that makes this even stranger. If spacetime is starting to crack, we need to ask the question that keeps physicists awake at night. What happens next? Does it collapse into something catastrophic? Or does it open doorways to physics we've never imagined? Michio Kaku has spent decades studying these possibilities. String theory suggests our universe might have hidden dimensions curled up so small we can't see them. But what if CERN's energy levels are finally high enough to stretch them open? What if these anomalies aren't measurement errors, but the first glimpses of reality's hidden architecture? Before we reveal what scientists think could form inside these potential cracks, make sure you hit subscribe so you don't miss the discoveries shaking physics to its core. Because what CERN detected in their latest spacetime test goes beyond anything they expected to find, and it's forcing us to rewrite the rules about what's possible in our universe. The data they collected isn't just challenging our theories. It's suggesting that the boundary between science and what we once thought was impossible might be thinner than anyone dared to imagine. Multiverse echoes. Now here's where Kaku's theories get truly mind-bending. He's not suggesting CERN opens some Hollywood portal to another dimension. What he's proposing is far more subtle, and far more scientifically plausible. Think about the early universe. In the first fraction of a second after the Big Bang, space itself was expanding faster than light. Physics tells us this cosmic inflation might not have been uniform everywhere. Different regions could have inflated at different rates, creating separate cosmic bubbles, each one becoming its own universe with slightly different physical laws. We live inside one of these bubbles. But what if other bubbles exist right alongside ours? Not accessible but close enough that their gravity could leak through. Kaku suggests CERN's high-energy collisions might be sensitive enough to detect these gravitational echoes, faint fingerprints from universes that exist just beyond the edge of our reality. The math actually supports this. Some models predict that particles created in CERN's collisions could briefly interact with gravitational fields from parallel universes. The effect would be incredibly tiny. But with 10 million billion collisions recorded, even tiny effects start to add up. Imagine throwing a stone into a lake. The ripples spread outward. But what if another stone was thrown from a different lake, and its ripples interfered with ours? That's one way some scientists describe how universes could overlap, and CERN might be sensitive enough to catch the tiniest trace of that interference. This isn't wild speculation anymore. Princeton physicist Lisa Randall has calculated how extra dimensions could affect particle behavior at LHC energies. Her equations show these effects would appear as subtle deviations in collision patterns, exactly the kind of anomalies CERN has been quietly documenting in their Run 3 data. But CERN isn't doing this alone. They've brought in an unexpected ally to push these questions further. If spacetime can be torn, someone has to model the damage. And CERN just brought in a tool that can do exactly that: quantum computers. Here's why this changes everything. Classical computers think in binary, on or off, 1 or 0. They're terrible at modeling quantum systems where particles exist in multiple states simultaneously. But quantum computers, they think like quantum particles. They can simulate the strange behavior of entangled particles, superposition, and yes, even theoretical wormholes. CERN partnered with IBM to test quantum machine learning on Higgs boson detection. The results shocked everyone. The quantum algorithm performed just as well as the best classical methods, and it did it using fundamentally different logic. But here's the breakthrough moment. In 2022, Google's quantum computer successfully simulated what they called a holographic wormhole. Not a real wormhole, but a mathematical model that behaved exactly like Einstein's predictions for how wormholes should work. The quantum computer created 2 entangled regions of spacetime, then it passed information through the connection, just like a tiny traversable wormhole would work in theory. Now CERN is scaling up these quantum simulations. They're not just analyzing collision data anymore, they're modeling what happens to spacetime itself during these high-energy impacts. This isn't science fiction. It's already happening. The question is, what happens if they scale it up? What if quantum computers can predict exactly where and when spacetime becomes vulnerable to these theoretical tears? And that's when the real mystery begins. Because CERN's latest data suggests they might have already found those vulnerable spots. Here's something that should terrify and fascinate you in equal measure. What if spacetime anomalies have already shown up in CERN's data? What if scientists are sitting on the discovery of the century, analyzing it in absolute silence until they're certain? This isn't conspiracy theory. This is how physics actually works. Remember 2011? The Opera experiment detected neutrinos apparently traveling faster than light. If true, it would have shattered Einstein's relativity. Time travel would become theoretically possible. Cause and effect would break down. But here's the key detail. Scientists didn't immediately announce they had broken physics. They spent months double-checking, triple-checking, running the experiment over and over. They finally published their results with a crucial disclaimer: they couldn't explain what they were seeing. They asked the global physics community to help verify or debunk their findings. It took 2 years to discover the truth: a loose fiber optic cable, a timing calibration error. The neutrinos weren't breaking light speed after all. But imagine if they had been. Imagine if that anomaly was real. The process would have been identical. Months of silent analysis, careful verification, no announcements until the evidence was absolutely undeniable. Now apply that same process to CERN's current data. If Run 3 experiments detected genuine spacetime irregularities, would we know about it immediately? Absolutely not. And let's be honest, would you announce to the world that you might have just bent reality if you weren't 100% sure? That's the kind of suspense hanging behind every collider run. CERN processes petabytes of collision data every year. Most of it confirms existing theories. But buried in those numbers could be signals that don't match any known physics. Signals that suggest spacetime isn't as rigid as we thought. The muon G2 anomaly took decades to confirm. The Higgs boson was theorized in 1964, but not discovered until 2012. Revolutionary physics moves slowly, carefully. Right now, there could be PhD students poring over collision data that shows reality bending in ways we never expected. But you won't hear about it until every alternative explanation is exhausted. And sometimes, Nature itself sends reminders that spacetime isn't as stable as we think. When the ground shakes, does spacetime shake with it? That question became very real in July 2025. A magnitude earthquake struck near CERN's facility. Nothing dramatic, just enough to rattle windows and knock a few books off shelves. But inside the Large Hadron Collider tunnel, the effects were immediate and unmistakable. The earthquake sent vibrations through the ground. These vibrations reached CERN's incredibly sensitive magnets. The proton beams started oscillating, wobbling back and forth in tiny, measurable patterns. For a brief moment, some observers wondered if they were seeing spacetime itself ripple. If the earthquake had somehow disturbed the fabric of reality in ways we'd never detected before. The truth was more mundane. A loose component called an RF finger had been shaken by the tremors. Engineers tracked down the mechanical issue and fixed it within hours. But here's what keeps physicists awake at night. If tiny earthquake vibrations can affect particle beams in measurable ways, what does that tell us about the stability of spacetime itself? Every high-energy collision sends shock waves through the quantum foam. Every particle creation event briefly warps the local geometry of space and time. We measure these effects indirectly through particle behavior. But what if some effects are too subtle for our current instruments? What if spacetime is constantly healing microfractures we can't even detect? The philosophical implications are staggering. If spacetime can ripple, tear, or shift, what does that mean for cause and effect? For the arrow of time? For free will itself? If reality's foundation is more flexible than we thought, then every decision, every thought, every collision at CERN might be reshaping the universe in ways we're only beginning to understand. But there's one more piece to this puzzle. Something that connects all these mysteries together and points toward a conclusion that will change how you see reality forever. Now, let's step back and get some perspective on these fears about CERN tearing spacetime. This isn't the first time people worried the Large Hadron Collider might break reality. When CERN first powered up the LHC in September 2008, lawsuits tried to shut it down. Protesters gathered outside the facility. Doomsday websites counted down to what they thought would be humanity's final day. The fear: microscopic black holes that would grow and devour Earth from the inside out. Michio Kaku was one of the scientists who stepped forward to calm public panic. He explained something crucial that most people didn't understand. Nature has been running its own version of the Large Hadron Collider for billions of years. Cosmic rays from deep space slam into Earth's atmosphere every single second. Some of these cosmic particles carry millions of times more energy than anything CERN can produce. If high-energy collisions could create dangerous black holes, cosmic rays would have already done it many times over. We're still here. CERN's safety studies put it bluntly: whatever the LHC will do, nature has already done many times over. But Kaku's response to these fears reveals something fascinating about his approach to physics. He balances wild imagination with scientific pragmatism. Yes, he speculates about wormholes and extra dimensions. String theory, which he helped develop, thrives on the idea of hidden spatial dimensions curled up smaller than atoms. But when pressed about CERN's real dangers, Kaku consistently returns to evidence. In 2008, he compared LHC fears to the panic over Halley's Comet in 1910. People thought Earth would be poisoned by gases in the comet's tail. Nothing happened. In 2011, when the faster-than-light neutrino anomaly emerged, Kaku explained why it was probably wrong before it was officially debunked. He understood the implications. If particles could exceed light speed, time travel becomes possible. Since this is ridiculous, he said, channeling Einstein, you cannot go faster than light. So yes, CERN has been called a doomsday machine more than once, but each time the Earth kept spinning and scientists kept peeling back the layers of mystery. That's the real drama here. This pattern reveals something important about how breakthrough physics actually works. The most revolutionary discoveries often start as tiny anomalies in data, signals that don't quite fit existing theories. The Higgs boson showed up first as a small bump in collision statistics. Dark matter reveals itself only through its gravitational effects on visible stars and galaxies. If CERN ever does detect genuine spacetime irregularities, they'll probably appear the same way, not as dramatic portals or reality-shattering explosions, but as subtle patterns that force us to rewrite our understanding of how the universe works. So here's the truth about CERN and spacetime. They haven't torn a hole in reality. But every collision, every data point, every anomaly brings us closer to finding the edges of what's possible in our universe. Whether it's quantum foam revealing the granular nature of spacetime, gravitational echoes from parallel universes, or subtle signs that reality itself has stress fractures we never knew existed, CERN is pushing human knowledge to its absolute limits. And that's what makes this story so compelling. We're not just talking about abstract physics happening in a tunnel beneath Switzerland. We're talking about humanity's relentless drive to understand the deepest mysteries of existence. Every time CERN fires up the Large Hadron Collider, we're asking the universe fundamental questions. How did everything begin? What are we made of at the smallest scales? Are we alone in the cosmos? Do other universes exist alongside our own? Michio Kaku has spent his career dreaming about the answers to these questions. His speculation about spacetime tears isn't fear-mongering, it's wonder. It's the recognition that our universe might be far stranger and more beautiful than we ever imagined. If the fabric of reality can tear even just a little, then maybe our universe isn't as permanent as we think. Maybe the boundary between impossible and inevitable is thinner than we ever dared believe. And that thought is both terrifying and awe-inspiring. It means we live in a cosmos where anything might be possible, where the next collision, the next data analysis, the next quantum simulation might reveal secrets that transform how we see our place in reality. What do you think CERN will discover next? Drop your thoughts in the comments. And don't forget to subscribe so you're here when the next breakthrough shakes our reality. Because if there's one thing we've learned from following CERN's journey, it's that the universe always has more surprises waiting for us. And some of those surprises might just redefine what it means to exist in this strange quantum, possibly infinite cosmos we call home.